Imagine drifting through the silent expanse of space when suddenly your radio telescope picks up something strange, a pulse, a burst, a signal so unusual it defies all known explanations. That's exactly what happened in August 1977 when the Big Ear radio telescope in Ohio captured the now famous WOW signal, a 72-second blast of radio waves so powerful, so inexplicable, that the astronomer who discovered it scrawled, "Wow." Right on the printout, decades later, we still don't know what caused it. Was it a natural cosmic phenomenon or something far more extraordinary? This is just one of the countless mysteries lurking in the depths of our galaxy. Across the universe, scientists have detected bizarre signals repeating bursts, eerie patterns, even pulses that seem to follow a logic we can't yet comprehend. Some vanish as quickly as they appear, never to be heard again. Others repeat with strange precision, like cosmic clockwork. And while many of these signals have scientific explanations, colliding stars, spinning neutron stars, or interstellar gas, some defy all logic, leaving even the brightest minds scrambling for answers. Could these be the faint echoes of distant civilizations? Or are we witnessing cosmic phenomena so rare, so unprecedented, that we've yet to even name them? In this exploration, we're diving deep into 30 of the most baffling galactic signals ever recorded, each one a puzzle waiting to be solved. From the chilling Lorimer burst to the mysteriously repeating fast radio bursts, we'll unpack the leading theories behind these cosmic whispers. Some point to the violent deaths of stars, others to the quirks of black holes, and yes, a few even suggest the tantalizing possibility of intelligence beyond Earth. But one thing's certain, every signal we uncover forces us to rethink what we know about the universe. So settle in, because by the end of this journey, you'll never look at the night sky the same way again. The cosmos is speaking. The only question is, are we ready to listen? That single burst of radio waves still haunts astronomers to this day. The WOW signal wasn't just strong, it was perfect. It hit the exact frequency scientists predicted an alien transmission might use, the hydrogen line at 1420 MHz, a quiet channel where cosmic noise fades and artificial signals would scream. For 72 seconds, it blazed across the Ohio sky before vanishing without a trace. The astronomer who found it, Jerry Amon, circled the data in red pen, his scribbled "Wow," capturing the shock rippling through the scientific community. But what could explain it? One leading theory points to comets specifically, the hydrogen clouds trailing them. In 2016, researchers proposed that two passing comets, unseen in 1977, might have belched massive hydrogen plumes, reflecting sunlight into the telescope's view. Yet critics pounced. Comets don't emit such focused, powerful bursts, and the signal's narrow frequency range defies natural explanations. Even stranger. Despite decades of monitoring, the signal never repeated, not once. Then there's the unsettling possibility. What if it was intentional? The signal's intensity suggests a source far more focused than any cosmic accident, almost like a lighthouse beam sweeping past Earth. Could it have been a fleeting hello from a civilization hundreds of light years away, their transmitter aimed at us for mere seconds before drifting off into the void? Or perhaps a long-dead alien probe, its final automated signal crossing the darkness before its power failed? The truth is, we may never know. The WOW signal remains a tantalizing enigma, a brief crackle in the cosmic static that rewrote our curiosity. It taught us one undeniable lesson: the universe is capable of surprises we're still unprepared to interpret. And somewhere out there, buried in the noise of space, another signal might be waiting, one we'll have to be ready to catch. The WOW signal didn't just fade into the cosmic background. It ignited a firestorm of curiosity that still burns today. Beyond its scientific intrigue, it became a cultural touchstone, a symbol of humanity's yearning to connect with something beyond ourselves. Movies, books, and even music have referenced it, embedding that cryptic "wow" scribble into the collective imagination. But for scientists, its legacy is even more profound. This singular burst reshaped the entire field of SETI, the search for extraterrestrial intelligence, proving that the universe could still deliver shocks we couldn't explain. Suddenly, the hunt for alien signals wasn't just speculative, it was urgent. Modern technology has turned the wow signal into a benchmark, a challenge to overcome. Telescopes like the Allen Telescope Array now scan the skies with unprecedented precision, hunting for repeats or patterns that might crack the mystery. In 2012, the Arecibo Observatory, before its tragic collapse, aimed its massive dish at the original wow coordinates, listening for echoes, silence. Even commercial projects like Breakthrough Listen, funded by billionaire Yuri Milner, have dedicated hours to the region, but the signal remains stubbornly, eerily quiet. Some researchers argue we're looking in the wrong place, that Earth's rotation or the signal's fleeting nature means we'd need an entire network of telescopes synchronized across the globe to catch it again. Yet the wow signal's greatest gift might be the questions it forces us to confront. If it was artificial, why hasn't it repeated? Could civilization send deliberate, one-time beacons like cosmic flare guns, hoping someone notices? Or was it merely a freak alignment of natural phenomena, a trick of the universe we haven't yet decoded? The signal's defiance has even birthed new theories, like the idea of Benford beacons, hypothetical alien transmitters designed to send brief, intense pulses to conserve energy. A concept physicist, James Benford, proposed to explain why we might hear a shout but never a conversation. For all our advances, the wow signal humbles us. It's a reminder that space isn't just vast, it's subtle. A single blip on a printout, decades old, still taunts us with possibilities. Whether it was a comet's whisper or a civilization's hello, it taught us to listen more carefully, to expect the unexpected. And as newer, stranger signals emerge from the void, the wow remains the gold standard, the mystery that set the bar for every cosmic "what was that?" yet to come. While the wow signal taunted us with its silence, another cosmic whisper did something far more intriguing. It came back. In November 2012, astronomers at the Arecibo Observatory detected a pulse so powerful it could outshine an entire galaxy for milliseconds. Catalogued as FRB 121102, this was no one-time mystery. Unlike other fast radio bursts that vanish after a single flash, this one kept repeating, spitting out furious bursts of energy in a pattern so erratic it defied all predictions. The source, a tiny, unassuming dwarf galaxy 3 billion light-years away, a place where stars are born in chaotic bursts. That distance alone is staggering. The signal began its journey when Earth was nothing more than single-celled organisms swimming in primordial soup. Yet what's truly baffling is the behavior. Some days FRB 121102 fires off multiple bursts in an hour. Other times it falls silent for months, as if playing a cosmic game of hide and seek. So what's causing it? One leading suspect is a magnetar, a neutron star with a magnetic field so intense it could strip the information off a credit card from halfway across the Milky Way. Picture this: the star's crust cracks under magnetic pressure, unleashing a shock wave that ripples through space, emitting these bizarre bursts. But there's a catch. Most magnetars calm down after a few outbursts. This one, it's been active for over a decade, its energy output bending the rules of known physics. Then there's the collision theory. Could two neutron stars locked in a deadly dance be generating these bursts each time they clash? It's possible, but the repeating nature throws a wrench in that idea. Collisions are violent, one-off events, not something you'd expect to repeat like clockwork. And then, of course, there's the elephant in the room. Could this be artificial? The idea isn't as far-fetched as it sounds. The burst's intensity and frequency mirror what we might expect from a colossal power source like a beacon or even propulsion technology from a civilization harnessing unimaginable energy. Astronomer Avi Loeb once speculated about alien megastructures, vast solar-powered transmitters that could explain the signal's precision. But until we find a pattern or a message buried in the noise, it remains a tantalizing what if. What makes FRB 121102 so extraordinary isn't just its repetition, it's the way it forces us to stretch our understanding of the cosmos. Every time we think we've pinned it down, it surprises us again, a reminder that the universe is always one step ahead. Whether it's a dying star's final tantrums or something far more extraordinary, one thing's clear: this little dwarf galaxy has a lot to say. And we're only just beginning to listen. One of the most puzzling aspects of FRB 121102 isn't just that it repeats, it's how it repeats. Unlike most cosmic phenomena which follow predictable rhythms, this fast radio burst behaves like a malfunctioning cosmic radio, switching between frantic activity and eerie silence without warning. But the real twist lies in its polarized emissions. When scientists analyzed the bursts, they found something extraordinary. The waves were twisted as if passing through an intense magnetic field. This polarization suggests the signal traveled through a turbulent, magnetized environment like the chaotic surroundings of a black hole or the turbulent winds of a neutron star. The location adds another layer of mystery. FRB 121102 originates in a dwarf galaxy with frenetic star formation, a place where massive stars live fast and die young, seeding the cosmos with dense remnants like magnetars. Yet, even among magnetars, this level of activity is unheard of. Typically, these ultramagnetic stars settle down after a few violent outbursts. This one, it's been firing off bursts for over a decade, as if fueled by an unseen energy source. Some theorists propose it could be a young magnetar, still flexing its magnetic muscles, while others suggest a more exotic scenario, a magnetar orbiting a black hole, its bursts amplified by the black hole's gravitational grip. Then there's the sheer power. Each burst lasts mere milliseconds, yet in that blink of an eye, it releases as much energy as the sun does in days. To produce such focused, intense emissions, the source would need to harness unimaginable forces. One explanation points to starquakes, sudden fractures in a neutron star's crust unleashing magnetic shockwaves. But even that struggles to account for the burst's erratic timing and polarized signatures. Perhaps the most tantalizing clue lies in what these bursts reveal about the universe itself. The polarization acts like a cosmic fingerprint, tracing the magnetic fields the signal passed through. By studying these twists, scientists can map the invisible magnetic scaffolding of intergalactic space, a frontier we're only beginning to explore. If FRB 121102 is a natural lighthouse, its beams are illuminating the hidden structure of the cosmos itself. Yet with every answer comes new questions. Why does this source behave so differently from other repeating FRBs? What's sustaining its activity long after similar objects would have burned out? Whether it's a celestial anomaly or something even more extraordinary, one thing is clear. FRB 121102 isn't just a mystery, it's a masterclass in cosmic unpredictability. And as we decode its secrets, we're not just listening to a distant galaxy's whispers. We're piecing together the universe's untold story, one burst at a time. Out of the countless radio signals scanned by SETI massive telescopes, one stands out not for its strength, but for its eerie precision. In March 2003, the Arecibo radio telescope locked onto a faint, rhythmic pulse emanating from a seemingly unremarkable patch of space near the constellation Pisces. Catalogued as a SETI 02+14a, this signal had all the hallmarks scientists had theorized an alien transmission might possess. It hovered around 1420 MHz, the same hydrogen line frequency as the WOW signal, a quiet band where cosmic noise fades and artificial signals would stand out starkly. But what made this detection so chilling wasn't just its frequency. It was the way the signal drifted. Unlike natural cosmic radio sources, which remain fixed in frequency, SHB 02 plus 14 are shifted ever so slightly over time. This drift rate matched what you'd expect if the signal came from a planet orbiting a distant star, its motion subtly altering the frequency as the transmitter moved toward and then away from Earth. Adding fuel to the fire, the signal originated near a known exoplanet candidate, a gas giant roughly twice Jupiter's size orbiting a sun-like star. The coincidence was striking. Had we accidentally tuned into a distant civilization's broadcast, skeptics were quick to dismiss it as interference, perhaps a malfunctioning earthly satellite or even a hoax. But the data told a more nuanced story. The signal's drift rate, while unusual for natural phenomena, wasn't impossible for human-made objects. Some argued it could have come from a high-altitude aircraft or a secret military experiment. Yet others pointed out that the signal's behavior didn't match any known terrestrial technology. It appeared and disappeared at random intervals, never repeating in a way that would simplify tracking. Then there's the location. The exoplanet near SHGB 02 plus 14 orbits its star at a distance that would make it far too hot for life as we know it. But what if the signal wasn't coming from the planet itself? Could it have been transmitted by a probe or relay station parked in that system, a piece of ancient technology still dutifully broadcasting into the void? The idea isn't pure speculation. In the 1960s, astrophysicist Ronald Bracewell proposed that advanced civilizations might deploy autonomous probes to communicate across interstellar distances, avoiding the lag of light speed delays. The truth is, we'll likely never know for certain. The signal vanished as mysteriously as it appeared, leaving behind only data plots and heated debates. But SHGB 02 plus 14 did something profound. It proved that even weak, ambiguous signals can challenge our assumptions. In the vast static of the cosmos, the line between natural wonder and artificial design is razor-thin. And as our telescopes grow more sensitive, the next signal might not be a question mark, but a revelation. Before fast radio bursts had a name, before they became one of astronomy's greatest puzzles, there was the Lorimer burst. In 2007, Duncan Lorimer and his student David Narkevic were sifting through old data from Australia's Parkes radio telescope when they stumbled upon something that shouldn't exist, a 5-millisecond spike of radio waves so powerful, it carried as much energy as 500 million suns. What made this discovery earth-shaking wasn't just its intensity, but its origin, a point billions of light years away, far beyond our Milky Way. In that fleeting moment, the universe had screamed. And then nothing. The signal, catalogued as FRB 010724, defied all expectations. Unlike pulsars or other known cosmic radio sources, this wasn't a repeating beacon. It was a cosmic gunshot firing once and vanishing forever. At first, some dismissed it as an instrumental glitch, perhaps a microwave oven used by Parkes staff interfering with the telescope as had happened before. But the data was undeniable. This burst came from deep space, its dispersion measure. The way its frequencies spread out revealing it had traveled through intergalactic plasma for nearly 3 billion years before reaching Earth. So what could unleash such staggering energy in mere milliseconds? One radical theory pointed to evaporating primordial black holes. These hypothetical relics from the Big Bang, theorized by Stephen Hawking, might explode in their final moments, converting their entire mass into a burst of radiation. Yet no such explosion has ever been observed, leaving the idea tantalizing but unproven. Others suggested cosmic strings defects in space-time left over from the universe's birth, snapping under tension and releasing colossal energy ripples. But these, too, remain in the realm of theory. The simplest explanation, a cataclysmic stellar collision. When two neutron stars spiral into each other, their merger could produce a magnetar with an ultra-strong magnetic field, capable of generating such a burst. But there's a problem. The Lorimer burst's energy dwarfs even these violent events. It's as if the cosmos handed us a puzzle piece that doesn't fit any existing picture. What made this discovery revolutionary wasn't just the mystery, it was the door it kicked open. Before 2007, astronomers didn't know such transient, energetic bursts existed. The Lorimer burst forced them to rewrite their playbook, proving the universe still held surprises that didn't just bend the rules, they shattered them. Today, hundreds of FRBs have been detected, each one building on that first accidental revelation. But none have matched the sheer shock value of that initial burst, the one that taught us to expect the unexpected from the silent, whispering dark. In October 2020, astronomers with the Breakthrough Listen project detected something extraordinary, a narrowband radio signal at 982 MHz, emanating from the direction of Proxima Centauri, the closest star to our Sun. Dubbed BLC-1, this signal checked all the boxes for a potential technosignature. It appeared only when the telescope was pointed at the star. It occupied a quiet slice of the radio spectrum free from natural interference, and it exhibited a slight frequency drift consistent with a transmitter on a moving exoplanet. Given that Proxima Centauri hosts at least one potentially habitable world, Proxima b, the discovery set off a firestorm of speculation. Had we just intercepted our neighbor's hello? The excitement was understandable. At just 4.2 light-years away, Proxima Centauri is practically next door in cosmic terms. Unlike the WOW signal or distant FRBs, any signal from this system wouldn't just be a relic of the distant past, it could be a near real-time communication, something we might even reply to within a human lifetime. The signal's narrowband nature deepened the intrigue. Natural cosmic phenomena like pulsars or quasars emit across wide frequency ranges. BLC-1, by contrast, was laser-focused, the kind of precision you'd expect from an engineered transmitter. Even skeptics admitted it was the most compelling candidate since the WOW signal. But science thrives on scrutiny, and within months the dream began to unravel. Further analysis revealed that the signal's frequency drift didn't quite match Proxima Centauri's motion. Instead, it aligned suspiciously well with oscillators found in earthly electronics. The smoking gun, the signal reappeared in follow-up observations, but only when human-made satellites or aircraft were in the telescope's field of view. By 2021, the team reached a sobering conclusion. BLC-1 was almost certainly interference, likely from a malfunctioning device or passing satellite. Yet the story doesn't end there. BLC-1's brief moment in the spotlight did something profound. It forced astronomers to confront the challenges of hunting for extraterrestrial signals in an increasingly noisy world. Our planet is now bathed in radio waves from cell phones, Wi-Fi, and satellites, creating a cacophony that telescopes must painstakingly filter out. The false alarm also highlighted a tantalizing truth. If a civilization were transmitting from Proxima Centauri, we're now technically capable of detecting it. The very fact that BLC-1 fooled experts proves our methods are sensitive enough to catch such a signal, should it ever arrive for real. Perhaps the most enduring legacy of BLC-1 is the way it refocused attention on our cosmic backyard. Before 2020, few would have guessed our nearest stellar neighbor might harbor a detectable technosignature. Now, Proxima Centauri sits at the top of SETI watchlist, a reminder that the answers we seek might be closer than we ever imagined. The universe is vast, but sometimes the most thrilling mysteries are right next door. In the quiet pre-dawn hours of August 1967, Cambridge graduate student Jocelyn Bell Burnell was scanning the skies when she noticed something odd, a series of rapid, rhythmic pulses beaming from deep space. Every 1.337 seconds, like cosmic clockwork, a burst of radio waves flickered across her charts. The signal was so unnervingly precise, so artificial in its regularity, that a team jokingly labeled it LGM-1, short for Little Green Men. For a fleeting moment, they dared to wonder, had they just intercepted an alien transmission? The truth was both more ordinary and more extraordinary. What Bell Burnell had discovered wasn't an interstellar telegram, it was the first pulsar, a rapidly spinning neutron star blasting beams of radiation across the cosmos like a lighthouse. These collapsed stellar corpses, no larger than a city yet denser than the sun, rotate at dizzying speeds, their magnetic fields funneling energy into tight beams that sweep past Earth with metronomic precision. Far from being alien broadcasts, pulsars turned out to be nature's most perfect timekeepers, some rivaling atomic clocks in their regularity, yet the story doesn't end there. Pulsar's very perfection raises a tantalizing question. Could an advanced civilization engineer something similar? Imagine a species wanting to announce its presence without revealing its location. A synthetic pulsar artificially stabilized to emit timed pulses would be the ultimate cosmic billboard. Unlike random radio bursts, a manufactured signal could mimic natural pulsar behavior flawlessly, hiding in plain sight among the galaxy's spinning neutron stars. Some theorists even suggest that certain pulsars with unusually stable frequencies, like the famous FRB 1919+21 Bell Burnell first detected, might warrant a second look. Could one of them be too perfect to be natural? There's a poetic irony here. The very signals that dashed hopes of alien contact in the 1960s might now serve as blueprints for how extraterrestrials could communicate. After all, if you wanted to build a beacon to last millennia, pulsars are the gold standard, their rhythms persisting long after their builders fade into dust. And that's the enduring lesson of the LGM episode. Sometimes the universe's greatest mysteries aren't just about what we find, but what we almost miss. The line between nature and artifice is thinner than we think, and in the vast cosmic silence, even the humblest star might be whispering secrets we're only beginning to decode. In the vast catalogue of cosmic oddities, few celestial objects have sparked as much debate and wild speculation as KIC 8462852, better known as Tabby's star. Located 1,500 light-years away in the constellation Cygnus, this unassuming flicker of light first made headlines in 2015 when astronomers noticed something inexplicable. It was dimming. Not in the gentle, predictable way planets cause when they transit their host stars, but in erratic, dramatic plunges, sometimes by as much as 22%. Imagine our sun suddenly darkening by a fifth with no clear explanation. That's the enigma of Tabby's star. The initial discovery made by citizen scientists combing through data from NASA's Kepler Space Telescope defied all conventional logic. Stars can dim for many reasons, passing planets, stellar companions, or even sunspots, but none of those fit. The dips were too sharp, too irregular, and too deep. One early theory pointed to a colossal swarm of comets, thousands of them, crossing the star's face in a chaotic parade. But calculations showed that even a comet army of that scale couldn't account for the staggering loss of light. Another idea suggested vast clouds of interstellar dust drifting between us and the star. Yet the star's light didn't redden as dust typically would, leaving that explanation on shaky ground. Then came the hypothesis that turned Tabby's star into a household name, the Dyson sphere. Proposed by physicist Freeman Dyson in the 1960s, these hypothetical megastructures would encase a star, harvesting its energy for an advanced civilization. Could the star's wild dimming be evidence of alien engineers building something unimaginably vast? The idea wasn't entirely far-fetched. A partial Dyson swarm, a network of orbiting solar collectors, might explain the irregular dips as massive panels drifted in front of the star. For a brief moment, the internet erupted with dreams of cosmic neighbors, but science thrives on skepticism. Further observations revealed the star wasn't just dimming erratically, it was also gradually fading over years, a phenomenon no known natural process fully explains. Some researchers proposed that the star might be consuming a planet, its death throws casting shadows across the cosmos. Others pointed to magnetic anomalies or undiscovered stellar physics. Yet with every new study, the mystery only deepened. Even the most exotic natural explanations struggled to account for all the star's bizarre behavior. What makes Tabby's star so compelling isn't just the unanswered questions, it's the way it forces us to confront the limits of our knowledge. Here was an object that didn't just defy expectations, it shattered them, revealing gaps in our understanding of stars, dust, and even the potential footprints of intelligence. Whether it's a swarm of comets, a cosmic catastrophe, or something far more extraordinary, one thing is certain. The universe keeps handing us puzzles that refuse to fit neatly into our textbooks. And sometimes the most profound discoveries begin with a single, inexplicable flicker in the night. If there's one thing the cosmos loves, it's a pattern except when it doesn't. Fast radio bursts have long been the rebels of the radio universe, flaring up at random, defying prediction. But in 2020, astronomers stumbled upon an exception to the rule. FRB 180916, a burst that doesn't just repeat, it keeps time. Every 16.35 days, like cosmic clockwork, this enigmatic source fires off a cluster of radio pulses before falling silent again. It's the first FRB ever caught in a predictable cycle, and its rhythm has scientists scrambling to decode what or who might be behind it. The leading theory points to cosmic choreography. Imagine a neutron star, one of the universe's most extreme objects, locked in a gravitational dance with a massive companion, perhaps a blue supergiant star or even a black hole. As the neutron star orbits, its powerful magnetic field interacts with stellar winds or debris from its partner, creating periodic bursts of energy. During part of its orbit, our view of the bursts might be blocked by the companion itself, explaining the regular silences. This binary system model fits the data neatly, suggesting the 16-day cycle mirrors the orbital period of the two objects. But there's a twist: not all bursts within the cycle are equal. For roughly 4 days, FRB 180916 erupts in furious activity, sometimes emitting multiple bursts per hour. Then, for the next 12 days, it goes quiet. This on-off switch hints at something more complex than a simple orbit. Some researchers propose the neutron star might be processing wobbling on its axis like a spinning top, its beams sweeping across Earth only during precise windows. Others suggest the companion star's own activity, like violent eruptions or magnetic storms, could be gating the bursts. Then, of course, there's the elephant in the room. Could this regularity be artificial? While natural explanations are far more likely, the precision is undeniably striking. If an advanced civilization wanted to broadcast its presence without revealing its location, a timed, repeating signal would be an elegant solution. The 16-day gap might allow them to conserve energy while ensuring the signal remains detectable across interstellar distances. Even more intriguing, the burst's location, a star-forming region in a nearby spiral galaxy, is exactly the kind of place you'd expect life to arise given enough time. What makes FRB 180916 so mesmerizing isn't just the mystery of its rhythm. It's the way it forces us to rethink the boundaries of natural phenomena. For centuries, we've looked to the skies for patterns, planetary orbits, pulsar beats, the steady flicker of variable stars. But this signal dances to a tune we've never heard before, a reminder that the universe's playlist is far stranger and more varied than we ever imagined. Whether it's a celestial pendulum or something even more extraordinary, one thing's certain: the cosmos has a flair for the dramatic, and this time it's working with a metronome. In September 2015, a Russian radio telescope scanning the cosmos locked onto something peculiar. a strong, narrowband signal pulsing from the direction of HD 164595, a sun-like star 94 light-years away in the constellation Hercules. Lasting just 2 seconds, the burst was unlike anything natural in that region. Most cosmic radio emissions are messy, spread across frequencies like static. This one, razor-sharp, centered on 11 GHz, a frequency with no known natural explanation. Even more intriguing, the signal's intensity suggested a source far more powerful than anything humanity could produce. If it originated from HD 164595, whatever generated it would have required energy on the scale of a Kardashev Type II civilization, a society capable of harnessing the total output of its star. The implications sent ripples through the scientific community. The Russian Academy of Sciences, typically cautious with such claims, flagged it as worthy of SETI follow-up. Astronomers at the SETI Institute scrambled their Allen telescope array to monitor the star for repeats. None came. Skeptics quickly pointed out alternative explanations, perhaps a passing satellite's reflection or interference from terrestrial radar. Even the signal's discoverer, astronomer Nikolai Bursov, tempered expectations, noting its strength could have been exaggerated if the source was much closer to Earth, like a military test or a glitching communications satellite. Yet the mystery lingers. HD 164595 isn't just any star. It's a near twin of our Sun, slightly older but similar in size and temperature. It also hosts at least one known planet, a Neptune-sized world orbiting too close for liquid water. But what if there are undetected planets farther out, or more provocatively, what if the signal wasn't a deliberate broadcast, but a stray emission from an alien megastructure or propulsion system? The 11 GHz frequency is notably used by human military and aerospace tech, raising eerie parallels. The signal's brevity makes it even more enigmatic. 2 seconds is barely a cosmic whisper, yet it echoes a troubling pattern in SETI. The most tantalizing signals are often the ones we can't verify. Whether it was a technological hiccup or a genuine cosmic hello, HD 164595 spike is a reminder of how thin the line is between discovery and dead end. And in the silence that followed, we're left with a haunting question. Was that blip a fluke or a fleeting glimpse of something far greater? For years, astronomers chasing fast radio bursts found themselves haunted by a bizarre cosmic imposter. Signals that looked exactly like FRBs but came with a glaring problem. They weren't cosmic at all. Dubbed Puritans after the mythological stag-bird hybrids that couldn't be confined to a single form, these bursts had all the hallmarks of genuine deep space phenomena. Intense, millisecond-long pulses of radio waves scattered across frequencies just like real FRBs. But there was one crucial difference. Every single one originated inside Earth's atmosphere. The mystery gnawed at researchers until 2015, when a team at Australia's Parkes Observatory cracked the case. By sheer accident, they discovered the culprit: microwave ovens. Staff members warming their lunches had unknowingly been generating bursts of interference when opening the oven doors mid-cycle, releasing a sudden surge of radiation that the telescope mistook for a cosmic event. The Puritans weren't alien messages or exotic astrophysics. They were hungry astronomers, impatiently interrupting their microwave's timer. What seemed like a comical blunder turned out to be a watershed moment for radio astronomy. The Puritans exposed a critical blind spot in how we search for cosmic signals. Before their discovery, observatories often treated interference as a nuisance to filter out, not a mimic capable of perfectly impersonating FRBs. But once the microwave connection was proven, researchers developed stricter protocols. Telescopes now monitor local radio noise in real time, cross-referencing signals with environmental data to weed out terrestrial fakes. Even the slightest blip from a passing airplane or a flickering power line can be flagged and dismissed, ensuring only genuine cosmic bursts make the cut. The legacy of the Puritans isn't just about better microwave etiquette, it's a lesson in humility. The universe is messy and our tools are imperfect. For decades, we assumed the biggest challenges in SETI would come from deciphering alien languages or decoding complex signals. Instead, some of the hardest puzzles are right here at home, teaching us to listen more carefully, question more deeply, and never take a cosmic signature at face value. After all, if a lunch break can masquerade as a message from the stars, what else might we be missing in the noise? When astronomers announced the discovery of Gliese 581G in 2010, the world held its breath. Here was a planet roughly 3 times Earth's mass, orbiting snugly within the habitable zone of its red dwarf star, a place where liquid water and perhaps life could exist. But 2 years earlier, something even more extraordinary had briefly flickered across the scientific radar. In 2008, a team searching for extraterrestrial intelligence reported detecting a mysterious laser-like pulse seemingly originating from the same star system. Lasting just milliseconds, the signal bore the hallmarks of an artificial beacon, a fleeting flash of light perfectly timed to stand out against the cosmic background. For a moment, it seemed humanity might have stumbled upon its first confirmed interstellar hello. The excitement was short-lived. Further analysis revealed critical flaws in the detection. The laser pulse had been observed only once, never to repeat despite extensive follow-up searches. More damningly, the signal's frequency matched known interference patterns from Earth's own atmosphere, likely a stray reflection from satellite debris or high-altitude aircraft. By 2012, even the original researchers conceded it was almost certainly a false alarm, a cosmic mirage born of wishful thinking and technological gremlins. Yet the Gliese 581G episode left an indelible mark on SETI. It forced a reckoning with the challenges of distinguishing true signals from noise in an increasingly crowded radio spectrum. The star's status as a potentially habitable system added fuel to the fire, demonstrating how easily hope could outpace evidence. Critics argued that announcing unverified detections risked eroding public trust, while proponents countered that transparency, even about false alarms, was essential for scientific progress. What makes this controversy so revealing isn't just the debunked signal, but the philosophical rift it exposed. Should SETI focus its limited resources on stars like Gliese 581G, where conditions seem ripe for life? Or is that approach too narrow, potentially overlooking civilizations adapting to environments we can't yet imagine? The failed laser pulse became a cautionary tale, but also a catalyst. Today, next-generation telescopes like the Vera Rubin Observatory are preparing to scan thousands of similar systems, armed with better tools to filter out earthly interference. The lesson of Gliese 581G wasn't to stop looking. It was to look smarter, with eyes wide open to both possibility and skepticism. Because in the end, the biggest discoveries often begin not with answers, but with questions we dare to ask. While Tabby's star captivated astronomers with its bizarre, unpredictable dimming, radio telescopes listening for accompanying signals heard something just as striking: nothing. Despite years of scrutiny from facilities like the Green Bank Telescope and the Allen Telescope Array, no unusual radio emissions have been detected from the star. This radio silence is perplexing. If an advanced civilization were constructing megastructures around Tabby's star, why wouldn't they also produce detectable radio leakage or intentional broadcast? The disconnect between optical oddities and silent radio waves opens a fascinating debate about how hypothetical extraterrestrial engineers might operate or hide. One possibility is that advanced civilizations abandon radio communication entirely. Think of humanity's own trajectory. Within just over a century, we've shifted from radio broadcasts dominating the airwaves to fiber optic cables and encrypted digital networks. A society millennia ahead of us might have moved beyond electromagnetic signals altogether. relying instead on neutrino messaging, quantum entanglement, or other technologies we can't yet detect. Radio could be as obsolete to them as smoke signals are to us, leaving their megastructures visible while their communications remain invisible. Alternatively, they might be deliberately avoiding detection. The concept of radio stealth isn't just science fiction. Military operations on Earth already use tight beam transmissions to minimize interception. A civilization wary of attracting attention could confine their signals to directional laser pulses or bury their communications in natural background noise, making them indistinguishable from cosmic static. There's also the chilling zoo hypothesis, which suggests advanced societies might intentionally avoid contacting younger species like us, observing quietly instead a cosmic prime directive rendering their presence nearly undetectable. Then there's the engineering angle. If Tabby stars' dimming stems from energy-collecting megastructures, the builders might prioritize efficiency over communication. Dyson swarms, for example, could be automated, operating for eons without organic overseers. Silent, self-sustaining machines wouldn't need to broadcast, they just harness the star's power and store it, leaving no electronic footprint for us to find. The absence of radio signals doesn't disprove the megastructure hypothesis, it complicates it. Tabby's star challenges us to rethink not just how we search for extraterrestrial intelligence, but what we're even looking for. The universe might be full of civilizations so advanced, their presence is written in starlight rather than radio waves, and that realization changes everything. If we're waiting for a cosmic hello in frequencies they no longer use, the greatest discoveries might be hiding in the silence. In July 2017, headlines around the world erupted with a claim that sent Star Trek fans and scientists alike into a frenzy. Radio astronomers had allegedly detected a signal from Vulcan, the fictional homeworld of Mr. Spock. The story spread like wildfire. A team in Louisiana had picked up an unusual radio burst matching the coordinates of HD 296515, the real-life star orbited by the hypothetical planet Vulcan in Star Trek lore. Social media lit up with jokes about interstellar diplomacy while tabloids breathlessly speculated about first contact. There was just one problem: the signal didn't exist. The hoax's origins were almost as bizarre as its fallout. A science blogger, riffing on the star's pop culture connection, jokingly suggested the fictional planet might explain recent exoplanet discoveries in the system. Within hours, the joke mutated into breaking news, with outlets repackaging the satire as fact. Even reputable platforms briefly stumbled, scrambling to retract stories after realizing they'd been duped by a perfect storm of wishful thinking and algorithmic amplification. The episode laid bare an uncomfortable truth: in the race for clicks, scientific rigor often takes a backseat to sensationalism. But the Vulcan signal hoax wasn't just a media embarrassment. It exposed a deeper vulnerability in how we process scientific discovery. The public's appetite for cosmic mysteries is insatiable, and the line between hypothesis and headline grows thinner by the day. Consider the parallels to real discoveries. When scientists announced Oumuamua, the first interstellar visitor, wild theories about alien probes overshadowed its likely natural origins. The same pattern played out with Tabby's star and its speculated megastructures. In an era where every anomaly sparks speculation, the Vulcan hoax became a cautionary tale about confirmation bias, our eagerness to see what we want to see in the stars. The fallout had real consequences. Astronomers working on legitimate SETI projects found themselves fielding questions about fictional Vulcan transmissions instead of discussing genuine research. Funding bodies grew wary of public backlash, while scientists lamented the erosion of trust in their field. Yet, ironically, the hoax also revealed something hopeful: people care. The public's hunger for cosmic connection is so strong, they'll latch onto even the flimsiest thread. The challenge moving forward isn't damping that enthusiasm, it's channeling it toward real science with all its careful checks and balances. Perhaps the most enduring lesson of the Vulcan signal is how easily fiction bleeds into reality when we stare too long at the cosmos. The universe is strange enough without inventing mysteries, black holes that sing, stars that flicker like dying light bulbs, radio bursts that repeat with mathematical precision. These are the true wonders worth chasing, not manufactured headlines, because in the end, the greatest discoveries won't come from hoaxes or hype, but from the patient, unglamorous work of listening, really listening to what the universe is trying to tell us. While most cosmic mysteries come in the form of light or radio waves, some of the universe's greatest puzzles reveal themselves through sheer movement, an invisible tug warping the paths of entire galaxy clusters. This is the enigma of dark flow, a bizarre phenomenon first detected in 2008 when astronomers studying the cosmic microwave background noticed something unsettling. Hundreds of galaxy clusters, each containing thousands of galaxies, were all streaming in the same direction at baffling speeds over 2 million miles per hour, as if pulled by some unseen force beyond the observable universe. The discovery sent shockwaves through cosmology. According to our current understanding, the universe's expansion should distribute matter evenly, with galaxies drifting apart in a stately, predictable dance. But dark flow defies that logic, suggesting something massive, something outside our cosmic horizon, is exerting a gravitational pull powerful enough to move entire clusters like leaves caught in a river's current. One radical explanation points to the multiverse. If our universe is just one bubble in an infinite cosmic foam, neighboring universes might lie tantalizingly close, their gravity leaking across the void. The dark flow could be the imprint of a parallel cosmos, a titanic structure lurking just beyond the edge of our sight. Critics argue the anomaly might stem from incomplete data or unknown quirks in the cosmic microwave background. Others propose a simpler culprit, an enormous concentration of mass, a supercluster so vast it bends space-time on scales we've yet to map, but even that raises questions. For such a structure to exist, it would need to dwarf anything in our known universe, challenging models of how matter clumps together after the Big Bang. What makes dark flow so mesmerizing isn't just the mystery, it's the way it forces us to confront the limits of our cosmic vision. We're like sailors on a vast ocean, sensing a distant tide but unable to see the shore. Whether the answer lies in parallel dimensions, hidden mass, or something even stranger, one thing's certain: the universe is still full of shadows, and in those shadows, the boldest ideas take flight. In 1974, scientists at the Arecibo Observatory did something unprecedented. They beamed humanity's first intentional radio message to the stars. Designed by astronomer Frank Drake and Carl Sagan, the Arecibo message was a binary-coded masterpiece, packed with information about Earth's location, human biology, and our understanding of chemistry. Aimed at the distant star cluster M13, 25,000 light-years away, it was more symbolic than practical, a cosmic hello in a bottle tossed into the ocean of space. But 27 years later, something astonishing happened. In 2001, a crop circle appeared in a field near the Chilbolton Radio Telescope in England, bearing an uncanny resemblance to the original Arecibo transmission, only this time it was altered. The human figure was replaced with a larger-headed being, the DNA helix tweaked, and the planetary diagram reconfigured to show an alien solar system. The world held its breath. Had someone or something answered, the truth was both simpler and more unsettling. The reply was an elaborate hoax crafted by terrestrial artists using ropes and wooden planks to flatten crops into precise patterns. But what made the Chilbolton message so chilling wasn't its authenticity. It was how convincingly it mimicked the structure of the original. The hoaxers had meticulously studied the Arecibo binary code, modifying it just enough to suggest an otherworldly origin while maintaining enough consistency to appear plausible. Their work exposed a glaring vulnerability in our assumptions about interstellar communication. If humans could fake an alien message this well, how would we ever recognize a real one? Decoding hypothetical alien signals is far harder than we imagine. Unlike Hollywood's visions of sleek alien scripts or universal mathematical constants, real extraterrestrial communication might be utterly alien, structured around senses we don't possess, concepts we've never conceived, or even non-linear time perception. Take the Arecibo message binary code. It relies on humanity's shared understanding of ones and zeros, but what if another civilization communicates through quantum states or fractal geometries? Even their alphabet might be unrecognizable, let alone the meaning behind it. Then there's the problem of context. The Arecibo message included a diagram of our solar system, but assume aliens receive it. Would they recognize it as a map or misinterpret it as art, a warning, or something entirely different? Human symbols, like an outstretched hand for peace, might signify aggression or indifference to another species. Without a shared evolutionary history, even basic concepts like friend or danger could get lost in translation. The Chilbolton hoax did more than fool a few UFO enthusiasts. It revealed the fragility of our cosmic communication strategies. If we can't distinguish between a human prank and a genuine alien reply, how prepared are we for the real thing? The universe might be full of voices, all shouting in languages we're only beginning to imagine. And until we learn to listen differently, we risk missing the message entirely. In July 2017, astronomers at the Arecibo Observatory turned their attention to a quiet red dwarf star just 11 light-years away, Ross 128. What began as a routine observation quickly spiraled into one of the most puzzling SETI detections in decades. The star, known for its occasional flares, did something unexpected. It emitted a series of bizarre, narrowband radio bursts that looked anything but natural. The signals appeared only when telescopes pointed at Ross 128, pulsating with a strange, almost rhythmic cadence. Even more intriguing, the bursts clustered around frequencies between 4,000 and 5,000 megahertz, a range cluttered with human-made interference, but also one where an intelligent civilization might logically transmit. For a brief, electrifying moment, researchers dared to wonder if they'd stumbled upon a beacon. The excitement was short-lived but revealing. As telescopes around the world scrambled to monitor the star, a team led by University of Puerto Rico Professor Abel Mendez uncovered a far more mundane explanation. Ross 128's flares weren't alien radio transmitters. They were the result of coronal mass ejections, violent eruptions from the star's surface. But here's the twist: these weren't ordinary solar flares. The star's tumultuous magnetic fields had twisted the bursts into unusual polarization patterns, mimicking the tightly focused signals of artificial origin. Even seasoned astronomers were fooled. The incident exposed a gap in our understanding of stellar behavior. Some red dwarfs, it turns out, can produce flare imposters sophisticated enough to impersonate technology. This ambiguity is at the heart of modern SETI's greatest challenge. The universe is noisy, filled with natural phenomena that blur the line between coincidence and design. Pulsars spin with clockwork precision. Magnetars unleash bursts that outshine galaxies. Now add Ross 128's flares to the list, a cosmic ventriloquist throwing its voice into the static. The star's antics forced astronomers to refine their detection protocols, implementing stricter checks to filter out stellar mimicry. One key lesson: duration matters. Artificial signals often persist or repeat predictably, while natural flares tend to be erratic. Yet even that rule isn't foolproof, as some stars like Ross 128 prove stubbornly adept at masquerading. Beyond the scientific implications, the Ross 128 episode raises a profound philosophical question. If a relatively nearby star can so convincingly mimic intelligence, how many false alarms litter the cosmos? Every unexplained signal carries the weight of possibility, but also the risk of chasing stellar ghosts. the cosmos seems almost playful in its ability to keep us guessing, dangling cosmic carrots just out of reach. Yet for all the false starts, each near miss sharpens our tools and our instincts, because somewhere amid the noise, the universe might finally drop the act and send a signal so unmistakable, even the skeptics will have no choice but to listen. Fast radio bursts have long been the universe's most enigmatic one-hit wonders until they weren't. Among the hundreds of these cosmic flashes detected, a select few defy the norm by repeating their performances on loop, turning what should be fleeting anomalies into persistent puzzles. Take FRB 121102, the celebrity of the repeating FRB world. Unlike its single-burst cousins, this one fires off clusters of pulses in erratic fits and starts, sometimes erupting multiple times an hour before vanishing for months. Then there's FRB 180916, the celestial metronome, ticking away bursts every 16.35 days with uncanny precision. What makes these repeaters so baffling isn't just their behavior, it's how different they are from each other. FRB 121102 hails from a turbulent dwarf galaxy, a stellar nursery where chaos reigns, while FRB 180916 originates in a quieter spiral galaxy, its rhythm suggesting an orderly orbital dance. This stark contrast hints that repeating FRBs might not have a single universal cause, but rather arise from multiple cosmic pathways. One leading theory for repeaters points to magnetars neutron stars with magnetic fields so intense they could atomize a credit card from halfway across the galaxy. When these stars experience starquakes, fractures in their crusts, the resulting shockwaves might generate the bursts. But here's the catch: most magnetars flare violently only in their youth before settling down. So why do some, like FRB 121102, keep crackling with activity years later? Some researchers speculate these magnetars might be trapped in tumultuous relationships, orbiting black holes or engulfed in debris clouds that continuously fuel their outburst. Then there's the binary system model, especially fitting for the clockwork rhythm of FRB 180916. Picture a neutron star locked in orbit with a massive companion, its bursts flaring predictably as it plows through stellar winds or grazes the edges of an accretion disk. Each close pass could trigger a fresh round of eruptions, like a cosmic lighthouse flickering on schedule. But the most tantalizing question remains: why do some FRBs repeat while others vanish forever? The answer might lie in their power sources. Non-repeating bursts could be the death cries of catastrophic events, neutron star collisions, collapsing black holes, or evaporating primordial cosmic strings. These one-off cataclysms would leave no encore. Repeaters, on the other hand, might stem from objects that survive their own violence, like magnetars or binary systems, allowing them to fire again and again. Or perhaps the distinction is simpler: geometry. A non-repeating FRB could be a cosmic bullet fired just once in our direction, while repeaters might have beams that sweep across Earth periodically like a rotating spotlight. If that's true, even the silent majority of FRBs could be repeaters. We just haven't been in the path of their beams long enough to catch an encore. Whatever the truth, these repeating signals force us to confront the limits of our cosmic imagination. They're not just flashes in the dark, they're riddles wrapped in magnetism, spinning at the edge of known physics. And with every new repeater discovered, the universe seems to be asking, how well do you really understand me? When Oumuamua streaked through our solar system in 2017, it wasn't just the object's bizarre shape that sparked fascination, it was the eerie quiet that followed. As the first confirmed visitor from interstellar space, this cosmic interloper seemed like the perfect candidate for a cosmic eavesdropping campaign. Telescopes around the world swiveled to listen, straining for any hint of artificial radio signals. Yet all they heard was silence, for an object that defied natural explanations, accelerating without a visible comet tail, tumbling end over end like a discarded rocket booster. the lack of detectable transmissions only deepened the mystery. If Oumuamua wasn't sending signals, did that rule out an artificial origin? Or might its silence be telling us something even stranger? One possibility is that Oumuamua wasn't designed to communicate. Imagine an interstellar probe programmed for pure reconnaissance, drifting between stars to collect data without announcing its presence. Human space missions already employ similar protocols. NASA's New Horizons probe, for instance, spends most of its journey in low-power hibernation, waking only periodically to transmit findings. An alien equivalent might prioritize stealth, conserving energy by avoiding unnecessary broadcasts. Alternatively, its communication systems could operate on principles we haven't yet imagined, using neutrino beams, quantum entanglement, or frequencies outside our current detection range. After all, if an advanced civilization wanted to study us undetected, they wouldn't rely on technology easily picked up by our primitive radio telescopes. Then there's the question of timing. Oumuamua's passage was fleeting, its closest approach lasting mere weeks. Our efforts to scan it were rushed, limited by the narrow window before it vanished into the void. Even if the object had been transmitting, we might have simply missed its active periods. Consider how Earth's own deep space probes communicate: brief, scheduled bursts of data punctuated by long silences. Had Oumuamua's on cycles aligned with our off moments, its signals could have slipped through unnoticed, but the most unsettling explanation might be that we weren't the intended audience. Suppose Oumuamua wasn't a lone scout but part of a network, designed to relay information back to its point of origin rather than broadcast indiscriminately. Its transmissions could have been tightly focused, like a laser beam aimed at a specific star system far beyond our detection range. To nearby observers like us, it would appear mute, a cosmic stealth bomber slipping through the night. The silence surrounding Oumuamua doesn't disprove its potential artificiality. It reframes the debate. In a universe where advanced civilizations might value efficiency over hellos, the absence of noise could be as telling as any signal. Sometimes the most profound messages aren't spoken at all, they're hidden in the quiet. Among the countless pulsars scattered across the Milky Way, one stands out not just for its eerie emissions, but for the unsettling precision of its rhythm. Geminga, a dead star 600 light-years away in the constellation Gemini, doesn't just pulse with radio waves like its kin. It's a gamma-ray powerhouse, blasting out high-energy photons with the regularity of a Swiss watch. Discovered in 1972, this neutron star spins 4 times per second, its beams sweeping past Earth like a cosmic lighthouse. But here's where things get weird. Unlike most pulsars whose radio emissions dominate, Geminga is nearly silent in the radio spectrum. Instead, it speaks in gamma rays, some of the most precise, focused bursts ever recorded. The strangeness deepens when you examine the patterns. Geminga's gamma-ray pulses arrive with such clockwork consistency, they've become a calibration tool for space telescopes. Yet the energy behind these bursts defies easy explanation. Normally, pulsars slow down as they age, their rotations gradually decaying. Geminga, however, bucks this trend. Its spin rate remains unnervingly stable, as if something unseen is fine-tuning its rhythm. This anomaly has led a small but vocal group of researchers to propose an electrifying possibility. Could Geminga's precision be artificial? The idea isn't as outlandish as it first seems. Gamma rays are notoriously difficult to produce naturally in such focused, repetitive beams. One theory suggests Geminga might be a stellar engine, an ancient megastructure built by a long-vanished civilization to harness the pulsar's colossal energy. Picture a Dyson sphere not around a star, but around a neutron star, its interior lined with gamma-ray collectors or propulsion systems channeling the pulsar's power for interstellar travel. The stability of Geminga's spin could hint at artificial stabilization, like gyroscopes counteracting natural slowdown. Skeptics counter with natural explanations. Geminga might be surrounded by a debris disk or magnetized plasma torus, acting like a flywheel to regulate its spin. Its gamma-ray dominance could stem from an unusually strong magnetic field, funneling energy away from radio waves and into higher frequencies. But even these theories struggle to account for the sheer predictability of the pulses, or the fact that Geminga is one of the few pulsars emitting quasi-periodic gamma-ray flares, brief outbursts that flicker with near-mathematical regularity. Perhaps the most haunting clue lies in Geminga's silence. Most pulsars broadcast across multiple wavelengths, their radio screams echoing through the cosmos. Geminga, by contrast, whispers exclusively in gamma rays, a frequency range most civilizations wouldn't monitor closely unless they had reason to. It's as if this object was designed to be overlooked, its signal hiding in plain sight. Whether it's a natural oddity or something more profound, Geminga challenges our assumptions about what a dead star should be. In the end, its mystery lingers like the afterglow of a gamma-ray burst, brief, brilliant, and impossible to ignore. High above Earth's atmosphere, lurking in the perpetual darkness of space, conspiracy theorists claim an ancient alien satellite has been silently watching us for millennia. Dubbed the Black Knight, this supposed relic of extraterrestrial technology allegedly orbits our planet, its origins lost to prehistory. The myth took root in the 1950s when amateur radio operators reported puzzling echoes of their own transmissions' delayed signals that seemed to bounce off an unknown object in polar orbit. Newspapers ran wild with speculation, and by the 1960s the legend had crystallized. Humanity wasn't alone in the cosmos, and proof was circling overhead. But here's the reality check. Those mysterious radio echoes, they were almost certainly caused by a well-documented phenomenon called long-delayed echoes, where signals refract through Earth's ionosphere in unpredictable ways, creating phantom reflections. As for grainy photos touted as evidence of the Black Knight, most were later identified as thermal blankets lost during spacewalks or discarded debris from early satellite missions. The infamous satellite image that still circulates online, that's a cropped, misinterpreted shot of a thermal cover jettisoned during a 1998 space shuttle mission. Yet the enduring appeal of the Black Knight myth reveals something fascinating about how real orbital oddities can spiral into legends. Take, for example, the enigmatic WTF star, officially TSC 4007992224, whose erratic dimming patterns baffled astronomers until they realized it was likely a cloud of disintegrating moons or asteroids. Or consider the countless pieces of space junk that occasionally flare with sunlight, creating fleeting UFO sightings for ground observers. Even SpaceX's Starlink satellites, with their eerie train-like formation shortly after launch, have triggered waves of confusion and speculation. The line between mystery and misunderstanding is razor-thin in space. When Russia secretly launched the Cosmos 2495 satellite in 1974, its unusual tumbling motion sparked panic in NATO, who suspected it was a nuclear-powered surveillance platform. Decades later, declassified documents revealed it was merely a failed naval reconnaissance probe, yet another case of human secrecy fueling cosmic paranoia. So while the Black Knight is pure fiction, its legacy endures because it taps into a deeper truth. Space is full of genuine anomalies waiting to be explained. In an era where defunct rocket boosters, discarded astronaut gloves, and decades-old spy satellites still zip overhead, it's no wonder our imaginations sometimes outpace the evidence. The real wonder isn't mythical satellites, it's how the vast, silent theater of orbit keeps conjuring new riddles for us to solve. In 1961, astronomer Frank Drake scribbled a simple equation on a chalkboard that would shape humanity's search for cosmic neighbors for decades to come. The Drake equation was elegant in its ambition, a way to estimate the number of civilizations in our galaxy capable of communicating across the stars. Plug in the variables: stars with planets, planets that could support life, the odds of intelligence evolving, and the lifespan of a technological society. The result, a spectrum of possibilities from a lonely Milky Way to one buzzing with countless voices. Yet here's the haunting paradox. After 60 years of listening, we've heard nothing but silence. Not a single confirmed whisper from the cosmos. So what's going on? Did Drake's math lead us astray, or are we just terrible at eavesdropping? One glaring possibility is that we've overestimated the equation's most hopeful variables. Take the lifespan of civilizations, for instance. Drake assumed technological societies might persist for thousands or even millions of years. But what if the window is far narrower? Climate collapse, nuclear war, or runaway AI could snuff out civilizations before they ever beam signals into the void. The universe might be littered with the ghosts of civilizations that flared brightly, then vanished. Even if life is common, the odds of two species overlapping in time and technological capability could be vanishingly small. We might be like ships passing in an unimaginably vast night, our radio transmissions arriving long after their intended listeners have turned to dust. Then there's the problem of technology itself. When Drake formulated his equation, radio was the pinnacle of human communication. But what if advanced civilizations abandon radio waves entirely? Imagine a society just a few centuries ahead of us, using neutrino beams, quantum entanglement, or other technologies we haven't even conceived. Their signals would be as invisible to us as Wi-Fi would have been to Leonardo da Vinci. The universe might be teeming with chatter, all in languages we lack the tools to hear, but perhaps the most humbling answer lies in scale. The Milky Way spans 100,000 light-years, and we've barely scratched the surface in our search. Think of it like this: if the galaxy were an ocean, our efforts so far would amount to scooping up a single glass of water and declaring there are no whales. Even our most powerful telescopes can only monitor a fraction of the sky at any moment, and for limited frequencies. Signals might be flooding past us every second, brief, directional pulses we're not positioned to catch, like missing a friend's flashlight across a darkened continent. Yet for all the unknowns, the Drake equation's real gift isn't its answers, it's the questions it forces us to confront. Every silent year sharpens our methods, refines our tools, and reminds us that the universe owes us nothing. The equation isn't wrong, it's a mirror reflecting our own limitations. And somewhere in that uncertainty lies the thrilling possibility that the next signal, the one that changes everything, might already be racing toward us, light years away but drawing closer with every passing second. Among the countless frequencies astronomers could scan for alien signals, one range stands out as the cosmic equivalent of a public square, the so-called water hole. Nestled between the hydrogen line at 1420 MHz and the hydroxyl line at 1660 MHz, this quiet band of the radio spectrum represents something extraordinary: the natural emission frequencies of the two ingredients that make water, the universal solvent essential for life as we know it. The logic was poetic. If extraterrestrials wanted to send a message other civilizations might notice, we're better to whisper than in the spectral neighborhood of the very molecule that defines habitable worlds. Yet decades of listening at the waterhole have yielded only silence. Not a single confirmed signal has emerged from this celestial meeting place, despite targeted searches by projects like SETI Project Phoenix and the Allen Telescope Array. The absence is puzzling, given that water is likely a prerequisite for any technology-building species. Why wouldn't advanced civilizations flock to this frequency like interstellar diplomats gathering at a neutral zone? One possibility is that we've misunderstood the cosmic zeitgeist. The waterhole might seem like an obvious choice to us, but only because we're carbon-based life forms obsessed with our own chemistry. For a silicon-based species breathing methane oceans, water frequencies could be as irrelevant as the scent of earthbound rain. Or consider the practical limitations. The waterhole overlaps with Earth's noisy atmospheric absorption bands, forcing telescopes to peer through radio static. An alien civilization might prioritize clearer frequencies or entirely different communication mediums, optical lasers, gravitational waves, or something beyond our current physics. Then there's the timescale problem. The waterhole hypothesis assumes civilizations evolve on similar schedules, but the universe is 13.8 billion years old. A species that mastered radio a billion years ago might have moved on to technologies we can't yet detect, leaving the waterhole as abandoned as a prehistoric trade route. Even if they did broadcast there, their signals could have washed over Earth long before humans built radio telescopes, or might not arrive for another million years. But the most sobering explanation might be the simplest: we haven't listened long enough. Covering the entire waterhole range requires monitoring millions of narrowband channels simultaneously, a computational Everest even for modern telescopes. Most searches sample mere fractions of the spectrum for minutes or hours per target. It's like tuning a radio to one station every few years and concluding no one's broadcasting. The waterhole's silence isn't necessarily a rejection, it's a challenge. It asks us to question our assumptions, refine our tools, and confront the enormity of the cosmic conversation we're trying to join. Because if the universe is speaking, it might not be in the language we expect. The real signal could be waiting just outside our current frame of reference, in frequencies we've yet to consider or patterns we've yet to recognize. And that's the paradox of the search. Sometimes the most profound messages aren't the ones we hear, but the ones that make us realize how much we still have to learn. The WOW signal wasn't just a one-time cosmic fluke. It became a blueprint for false hope. Over the decades, multiple signals have emerged that seemed, at first glance, to echo its telltale signature. A narrowband radio spike at 1420 MHz, appearing briefly before vanishing into the void. In 2020, researchers using the Green Bank telescope locked onto a candidate dubbed WOW 2.0, a 70-second burst that matched the original's frequency almost exactly. The astronomy community buzzed with excitement, but within weeks the truth deflated the hype. The signal wasn't extraterrestrial, it came from a passing satellite, its frequency drifting as it crossed the telescope's field of view. This pattern repeats itself again and again. A signal in 2015 from the direction of HD 164595, initially hailed as a potential technosignature, turned out to be interference from an Earth-orbiting military satellite. Another in 2018, detected by the Parkes telescope, traced back to a malfunctioning microwave oven in the observatory's break room, the same culprit behind earlier Puritan false alarms. What makes these copycats so compelling isn't their authenticity, but what they reveal about our own psychology. Every time a signal fits the WOW template brief, narrowband, unexplained, it triggers a Pavlovian response in the scientific community and the public alike. We want to believe this confirmation bias shapes everything from how data is analyzed to which observations get funding. Researchers often prioritize monitoring stars where previous anomalies occurred, like a gambler fixated on a slot machine that nearly paid out once. The media, hungry for headlines, amplifies the cycle, turning technical glitches into potential alien contact before peer review can intervene. Even rigorous scientists aren't immune. When the Breakthrough Listen team detected BLC-1 from Proxima Centauri, their initial excitement led to a rushed press conference only for the signal to later be debunked as human-made interference. The deeper irony, the WOW signal itself might not have been as unique as we think. Modern analysis suggests similar bursts likely occur across the sky regularly, unnoticed because telescopes weren't pointed in the right direction at the right time. In a universe teeming with natural radio sources, pulsars, magnetars, colliding neutron stars, the line between extraordinary and mundane is razor-thin. The real lesson of these copycats isn't that we're bad at finding aliens, but that the cosmos excels at fooling us. Every false alarm refines our search, teaching us to distinguish cosmic whispers from the static of our own expectations. And somewhere in that process, we might just stumble upon a signal so unmistakable, even the skeptics will have to pause and say, wow. Most fast radio bursts vanish instantly, leaving only silence in their wake. But FRB 1905-20 refuses to play by those rules. Discovered in 2019 by China's 500-meter aperture spherical telescope, this cosmic rebel doesn't just flash and disappear, it lingers. Between its furious bursts, which last mere milliseconds, a faint but persistent radio glow hums in the background like a dormant engine waiting to rev again. This afterglow phenomenon sets it apart from nearly every other FRB we've catalogued, sparking urgent debates about what or who might be powering it. The leading natural explanation points to an extreme environment unlike anything in our cosmic neighborhood. Picture a neutron star shrouded in thick, magnetized plasma, the remnants of a supernova's aftermath or debris from a shredded companion star. As the star's beams punch through this turbulent shroud, they could excite the surrounding particles, causing them to emit a continuous radio whisper even during quiet periods. It's like a lighthouse surrounded by fog. Even when the beam isn't directly visible, the illuminated haze betrays its presence. This scenario might also explain why FRB 1905-20's bursts scatter more dramatically across frequencies than most, as if fighting through a cosmic filter. Yet there's a catch. Plasma that dense should dissipate over time, yet this source's glow has remained eerily steady since its discovery. Some theorists argue we might be witnessing something far rarer, a newborn magnetar, fresh from the stellar collapse that created it, still embedded in the dense nebula of its own birth. Like a screaming infant swaddled in the remnants of its celestial womb, the magnetar's outbursts would interact violently with this surrounding material, sustaining the glow between tantrums. Then there's the more speculative but irresistible possibility: artificial engineering. The persistent emission resembles what we'd expect from a colossal power source operating intermittently. Imagine an alien megastructure drawing energy from its host star, firing focused beams to communicate or propel vessels across interstellar distances. The between-burst glow could be the idling signature of machinery too vast for us to comprehend, like catching the hum of a city's power grid between flickering streetlights. Even the signal's location deepens the intrigue it hails from the outskirts of an ancient dwarf galaxy, a place where time has moved slower, granting any hypothetical civilization billions of extra years to develop beyond our comprehension. What makes FRB 1905-20 so mesmerizing isn't just the mystery of its glow. It's the way it forces us to confront the limitations of our cosmic imagination. Every time we think we've pinned down the nature of FRBs, an outlier like this one emerges, laughing in the face of tidy classifications. Whether it's a natural wonder or something more, its enduring whisper reminds us that the universe is under no obligation to make sense to us. And in that uncertainty lies the thrill of the hunt, because for every rule we establish, there's always an exception waiting to rewrite the playbook. The Breakthrough Listen project has spent years scouring the cosmos with some of Earth's most sensitive radio ears, and along the way, they've stumbled upon signals that made even the most seasoned astronomers pause. In 2017, the Green Bank telescope locked onto a bizarre emission from a star called Ross 128, a red dwarf just 11 light-years away. The signal pulsed at a frequency suspiciously devoid of natural interference, drifting in a way that mimicked a transmitter on a moving planet. For a breathless moment, researchers dared to wonder, had they finally intercepted our cosmic neighbor's call? But the truth, as always, was more complicated. When the team re-examined the data, they found the signal's drift rate didn't align with the star's motion. Instead, it matched the telltale signature of human-made satellites, their transmissions bouncing through the atmosphere like echoes in a canyon. This pattern of excitement and disillusionment is baked into Breakthrough Listen's DNA. Another tantalizing candidate, BLC-1, briefly fooled researchers in 2020 with its Proxima Centauri origin story until someone realized its frequency drift mirrored cheap oscillators found in earthly electronics. Then there was the case of the Puritans, those FRB impersonators later traced to impatient astronomers microwaving their lunches. Each false alarm follows a familiar autopsy, initial intrigue, mounting skepticism, and ultimately, the sobering realization that the universe is infinitely creative in its ability to mimic intelligence. But dismissing these signals isn't failure, it's science in action. Breakthrough Listen operates like a cosmic crime lab, subjecting every candidate to brutal cross-examination. Signals must pass the origin test, appearing only when the telescope points at a target star, vanishing when it looks away. They're checked against satellite databases, military radar logs, even local Wi-Fi networks. Some are interrogated with a technique called beam switching, where the telescope rapidly toggles between the star and empty sky, watching for inconsistencies. It's a gauntlet few anomalies survive, yet the process itself is revolutionary. By cataloging how nature and human tech can masquerade as aliens, researchers are building a playbook to recognize the real thing. Perhaps the most valuable lesson isn't in the signals they've caught, but the ones they've ruled out. Every dead end sharpens the search, teaching us to distinguish cosmic whispers from the static of our own noisy planet. And hidden in that meticulous winnowing might lie the key to uncovering a signal that refuses to be explained away, one that withstands every test, defies every filter, and forces us to reckon with the possibility that we're not just listening to the universe anymore, but finally hearing it talk back. The Puritans episode was more than just a cosmic prank. It became a turning point in how we listen to the universe. Before astronomers traced those microwave-induced bursts back to impatient lunch breaks, radio telescopes often treated interference as background noise to be filtered out, not a masterclass in deception. But the Puritans forced a reckoning. Their uncanny mimicry of genuine fast radio bursts exposed a blind spot in our search for cosmic signals. If something as mundane as a kitchen appliance could impersonate a deep space phenomenon, how many other false positives were slipping through? This wasn't the first time a red herring pushed science forward. In the 1960s, astronomers at Cambridge were baffled by flickering radio sources they nicknamed scruff. These turned out to be the first quasars' unimaginably bright galactic cores powered by supermassive black holes. What began as interference noise led to the discovery of the universe's most energetic objects. Even the famous WOW signal, still unexplained, sharpened SETI protocols, teaching researchers to prioritize repeatability over one-off anomalies. Each false alarm, each near miss, acts like sandpaper on the tools of discovery, wearing away assumptions until the true shape of reality emerges. The Puritans' legacy lives on in modern observatories, where algorithms now cross-reference every blip with environmental data, satellite trajectories, aircraft transponders, even local Wi-Fi networks. Telescopes like CHIME and FAST employ real-time machine learning to sift cosmic wheat from terrestrial chaff, a direct response to the microwave oven debacle. It's a layer of skepticism baked into the process, ensuring that the next time a signal seems too good to be true, science won't just ask, could this be aliens? But what's the least exotic explanation? Yet there's irony in this vigilance. The very filters designed to weed out false signals might one day screen out a genuine message. Imagine an alien civilization transmitting in a format that resembles human interference, perhaps using frequencies we've abandoned to avoid noise, or encoding their signals in patterns that mirror natural phenomena. The Puritans remind us that the line between artifact and artifact is razor thin, and sometimes progress isn't just about finding answers, but learning how to question the questions themselves. In the end, the universe's greatest trick might be its ability to keep us humble. Every time we build a better mousetrap for cosmic mysteries, the cosmos invents a smarter mouse. The Puritans weren't a setback, they were a gift, a lesson written in radio static. Listen carefully, but never stop doubting. Because somewhere in the noise between the false alarms and the dead ends, there might just be a signal waiting to rewrite history. The cosmic microwave background is often called the universe's baby picture, a faint afterglow from the Big Bang itself stretching across the entire sky. For decades, scientists treated it like a smooth, predictable canvas, the ultimate proof of cosmic uniformity. But then the anomalies started appearing. Tiny, inexplicable patterns in the data that refused to fit the standard model, like finding fingerprints on a photograph that's supposed to be pristine. One of the most puzzling is the so-called axis of evil, a mysterious alignment of temperature fluctuations in the CMB that seem to point in a preferred direction, as if the universe itself has a North Star. This flies in the face of everything we know about cosmic inflation, which predicts the early universe should have been perfectly symmetrical, with no favored axes or orientations. Yet there it is, a spine of asymmetry running through the cosmos like a crack in a mirror. Some theorists suggest this could be evidence of a pre-Big Bang structure, a fingerprint from whatever existed before space-time as we know it began. Others go further, proposing it's the gravitational imprint of a neighboring universe brushing against ours in the multiverse. Then there's the cold spot, a vast, eerie region in the CMB where temperatures dip far lower than any standard model can explain. Spanning nearly 2 billion light-years, this cosmic bruise could be the shadow of a supervoid, an unfathomably empty stretch of space where galaxies simply refuse to form. But even that explanation strains credibility. Voids that large shouldn't exist in our current understanding of structure formation. Alternative theories flirt with more exotic possibilities, a collision with a parallel universe, a defect in the fabric of spacetime itself, or even the remnants of a black hole from a previous cosmic cycle. What makes these anomalies so tantalizing is their scale. These aren't quirks in a distant galaxy, they're etched into the very foundation of reality. The CMB is our oldest, most universal dataset, and its glitches hint that the universe might be keeping secrets from us. Maybe inflation wasn't as uniform as we thought. Maybe the Big Bang wasn't the true beginning, just a reboot, or perhaps, and this is where it gets truly mind-bending, we're seeing the edges of something vaster, a multiverse where our cosmos is just one bubble in an infinite foam of realities. For now, these anomalies remain unanswered questions, cosmic breadcrumbs leading us toward horizons we're only beginning to imagine. Every new satellite, every more sensitive map of the microwave sky, brings us closer to understanding whether these are mere statistical flukes or the first whispers of a deeper truth. One thing's certain, the universe's baby picture has wrinkles we never expected, and those wrinkles might just rewrite the story of everything. After decades of scanning the skies for alien transmissions, one uncomfortable truth lingers: the universe is far quieter than it should be. Fermi's famous question, "Where is everybody?" echoes louder with each unexplained signal we detect. If intelligent life is common, why haven't we stumbled across irrefutable evidence? Why do cosmic whispers like the wow signal or repeating FRBs tease us with ambiguity rather than deliver clarity? This is the heart of the silent universe paradox, a riddle that forces us to confront whether we're alone or simply not listening correctly. One chilling explanation is the zoo hypothesis. Imagine Earth as a designated cosmic nature preserve, observed but deliberately isolated by civilizations far more advanced. Just as anthropologists might avoid contacting uncontacted tribes to preserve their natural development, extraterrestrial societies could be adhering to a galactic prime directive, keeping their presence hidden to allow humanity to evolve without interference. The signals we do detect under this model might be accidental, like overhearing a distant conversation not meant for our ears. Alternatively, consider the stealth economy of interstellar communication. Broadcasting signals across light years requires staggering energy. An advanced civilization might prioritize efficiency over visibility, using tightly focused laser pulses or neutrino beams instead of wasteful omnidirectional radio waves. Their transmissions could be as invisible to our current technology as fiber optic cables would have been to 18th century sailors. Even our own military satellites use frequency hopping and beamforming to avoid detection. Why wouldn't aliens refine similar tactics across millennia? Then there's the possibility of silent probes. The Breakthrough Starshot initiative aims to send gram-scale probes to Alpha Centauri at relativistic speeds, a technology that, if scaled up, could pepper the galaxy with self-replicating observatories. An ancient alien civilization might have long ago deployed such devices, camouflaged as asteroids or disguised as natural cosmic phenomena, quietly collecting data without announcing their presence. Oumuamua's strange acceleration and lack of radio emissions could fit this profile, a stealthy scout designed to observe, not announce, but the darkest answer might be time. The universe is 13.8 billion years old. Human civilization has existed for a cosmic blink. Entire civilizations could have risen, broadcast their existence for millennia, and vanished before Earth's continents even formed. The signals we so desperately seek might have washed over our planet while microbes still ruled the oceans, leaving no one to listen. Fermi's paradox assumes synchronicity, that other species are active when we are. But space isn't just vast, it's asynchronous. The silence we perceive might not be absence but bad timing. Yet for all these explanations, one uncomfortable truth remains. The more signals we discover without clear answers, the more the paradox deepens. Each unexplained burst or flicker could be a piece of the puzzle, or another red herring in a universe that excels at keeping its greatest secrets just out of reach. The cosmos may not be silent after all. We might just be straining to hear a conversation happening in a language we don't yet understand. For all the mysteries we've uncovered so far, the real revolution in cosmic eavesdropping is just getting started. Buried in remote deserts and atop wind-scoured plateaus, a new generation of telescopes is taking shape, machines so sensitive they could rewrite the rules of the search for alien intelligence. At the forefront is the Square Kilometre Array, or SCAR, a sprawling network of antennas spanning 2 continents. When completed in the next decade, its total collecting area will surpass 1 square kilometer, allowing it to detect signals 100 times fainter than current instruments can spot. But raw power isn't its only trick. SCAR's true genius lies in its ability to monitor billions of radio channels simultaneously, effectively scanning an ocean of frequencies where previous telescopes could only dip a toe. If someone out there is broadcasting on a frequency we haven't thought to check, or switching channels in patterns we've yet to decode, this behemoth stands the best chance yet of catching them in the act. Yet radio waves might be just the beginning. As we push the boundaries of detection, scientists are expanding the hunt into realms that would have seemed like science fiction just decades ago. Consider neutrinos, ghostly particles that stream through Earth by the trillions every second, barely interacting with matter. Unlike radio signals that ricochet off interstellar gas, neutrino beams could traverse the galaxy virtually unscathed, carrying messages across light years without distortion. Experiments like IceCube in Antarctica are already proving we can detect these cosmic phantoms. An advanced civilization might have mastered techniques to encode information in their subtle fluctuations. Then there's gravitational wave astronomy, still in its infancy since LIGO groundbreaking detection in 2015. Theoretically, an extraterrestrial society could manipulate spacetime itself, creating patterned ripples as unmistakable as Morse code in a pond. Imagine detecting a sequence of precisely timed gravitational pulses, a hello so fundamentally woven into the fabric of reality, it couldn't possibly be natural. Upcoming observatories like LISA, a space-based gravitational wave detector slated for the 2030s, might give us the sensitivity to spot such engineered spacetime tremors. The most tantalizing possibilities lie beyond even these frontiers. Some theorists speculate about quantum communications messages encoded in entangled particles where information transfer happens instantaneously, bypassing light-speed delays. Others imagine decoding signals hidden in the very structure of cosmic rays or the polarization patterns of light across interstellar distances. What if extraterrestrials have long since moved beyond clumsy radio broadcasts, embedding their presence in subtler signatures we're only beginning to conceive? This isn't just about building better receivers, it's about redefining what a signal even looks like. The technosignatures of tomorrow might not announce themselves with blaring radio horns, but in the quiet hum of particles, the faintest tremors in spacetime, or anomalies in data streams we've yet to think to monitor. As our tools evolve from crude radio ears to exquisitely tuned cosmic senses, we're not just expanding the search, we're learning to hear the universe in entirely new ways. Picture this: after decades of searching, an unmistakable alien signal finally crackles through our telescopes, mathematically precise, repeating, and clearly artificial. The world erupts in celebration, and then panic sets in. Who gets to speak for Earth? What do we say back? This is the contact protocol dilemma, a real-world problem hiding in plain sight behind all our interstellar daydreams. Right now, locked in desk drawers and secure servers, multiple conflicting plans exist for this exact scenario, with no global consensus on who should hold the microphone for humanity. The United Nations Office for Outer Space Affairs has vague guidelines suggesting international consultation, but they're about as enforceable as a schoolyard pact. Meanwhile, SETI-owned Declaration of Principles signed by major space agencies urges verification of any signal before response, but conveniently avoids specifying who drafts that response. The result, a bureaucratic Wild West where NASA, private initiatives like Breakthrough Listen, or even a rogue billionaire with a radio telescope could theoretically fire off Earth's first interstellar hello without oversight. Consider the chaos if multiple entities respond simultaneously. Imagine China transmitting Confucian philosophy while SpaceX beams corporate logos and amateur radio enthusiasts blast heavy metal. An intergalactic cacophony revealing not just our lack of coordination, but our deepest cultural divides. History offers sobering parallels. When European explorers first encountered indigenous civilizations, the absence of unified protocols led to catastrophic misunderstandings. Now scale that to cosmic proportions, where mistranslation could span light years and consequences last millennia. Even the scientific community is divided. Some argue only astrophysicists and linguists should craft messages, packing them with universal mathematics. Others insist philosophers and artists must lead, communicating human essence beyond cold equations. Then there's the militarized elephant in the room. Protocols drafted during the Cold War still classify certain signal responses as matters of national security in the U.S. and Russia, blurring lines between scientific discovery and strategic threat assessment. The irony is crushing. We've developed technology to hear the cosmos but haven't agreed how or if to whisper back. Perhaps the greatest signal we've already sent isn't radio waves, but this very indecision, revealing a species still learning to speak with one voice. As the chances of contact grow ever more tangible, our silence on Earth about how to respond screams louder than any message we might send to the stars. The universe may be listening closer than we think. From the fleeting whisper of the wow signal to the clockwork precision of repeating fast radio bursts, we've journeyed through 30 of the cosmos' most baffling transmissions, each one a riddle wrapped in static. Some, like the Lorimer burst, find plausible homes in the violent deaths of stars or collisions between neutron stars, cosmic echoes of unimaginable energy. Others, like the eerie polarization of FRB 121102, hint at magnetas tangled in chaotic magnetic webs, their outbursts twisted by forces we're only beginning to grasp. And then there are the outlier signals like SETI 02 plus 14a, drifting inexplicably, or Tabby's star's erratic dimming, which still defy tidy classification, dangling between natural wonder and the tantalizing specter of intelligence. But the real magic lies in the unsolved, the wow signals comet theory, plausible but unsatisfying, the precise rhythm of FRB 180916. A binary dance fits until you remember no known celestial mechanics explain its flawless timing. These gaps in understanding aren't failures, they're invitations. Every unexplained frequency, every anomalous flicker is a cosmic breadcrumb urging us to look deeper, question harder, and rethink what we know. Consider how far we've come. The same curiosity that turned pulsars from LGM suspects into natural lighthouses now trains AI on petabytes of radio data, hunting patterns no human eye could spot. The tools that once mistook microwaves for messages now filter the universe's noise with surgical precision. And yet, for every mystery we crack, two more emerge, each more perplexing than the last. That's the beauty of the cosmos. It doesn't give up its secrets easily. So keep looking up. The next great discovery might already be racing toward us, hidden in the next burst of static, the next flicker of a distant star. Whether it's a natural phenomenon beyond our wildest models or the first undeniable hello from another world, one thing's certain: the universe is anything but silent. It's shouting in a language we're still learning to speak, and the lesson isn't just to listen, but to stay endlessly, recklessly curious, because out there in the vast dark, the next signal is waiting. And when it arrives, it'll change everything.